guys, for coming out and being here. We have a session here sponsored by Sync Computing, so we have to welcome Jeff and Sean. We're going to talk about how they built Gradient to optimize Databricks cluster at scale.
Cool. Hey, everyone. Thanks for having us. I'm Jeff, co-founder and CEO of Sync Computing. We're a startup. We spun out of MIT a couple years ago, and we're excited to talk about how we built Gradient, a new product we released last week to help optimize Databricks clusters at scale. Before we kind of dive into this stuff, just a little bit about who we are. This is the team. We just raised our Series A last year, and the team is composed of a bunch of folks from a lot of great companies. And our roots are kind of embedded in kind of the academic world. It's kind of where we basically come from. So for this talk, I thought we would start on, what's the problem that we're trying to solve with Gradient, right? So there are typically 3 phases of company Databricks adoption that we've kind of seen across the board, right? So the first phase I would call the honeymoon phase. This is where everyone loves using Databricks. Notebooks are so easy. It's so great. It's wonderful. And this is kind of where a lot of folks start. And then phase 2, using the very technical term, the YOLO phase. This is where folks really start to kind of go all in on Databricks. They're like, scale up, build faster. We need products out. That's kind of the where companies really start to hit the gas on kind of scaling up their Databricks workloads. But this kind of behavior inevitably ends up in phase 3, which we call the tantrum phase. This is where typically your Databricks costs start skyrocketing, and a lot of folks start having a lot of issues with efficiency, and they're wondering, how do we scale back? But they don't want to change anything. They don't want to move anything. It's like, how do we do better with what we have today? So that's kind of what we do here at Sync. We're here to help companies basically avoid tantrums. Like, how do we get them out of that phase? So it's typically companies who are kind of nearing production or using kind of Databricks at scale is kind of where we're targeting. So there are many ways to kind of optimize cloud infrastructure, Databricks, et cetera. We are trying to target kind of the at the engineer level. Like, what can an individual data engineer do to kind of optimize their systems? And so, it's a very hard thing to optimize Databricks. Why? One of the biggest things is I don't know how to tune Spark. It's a very famous old problem. There are lots of Medium posts about tuning Spark. It's a very famous pain to kind of tune Spark. Another one is I don't know when my jobs need tuning. Who knows when they drift, get out of optimal points or not. That's very kind of hard to tell. Other big one is like you have other goals on top of cost savings. Like you just need a pipeline to work. I need to move. I don't really have time to focus on cost savings. And the last one is very relevant for a lot of kind of larger companies where they just have too many jobs. Some of the companies we're working with have hundreds, if not thousands, of Databricks jobs. And basically going in and tuning and optimizing each job is just untenable. So to kind of get into what am I talking a little bit about, right? A couple just kind of very narrow points just based on some internal studies that we did with the TP-CDS workload. One thing that's hard is like cluster scaling is really hard to figure out. For example, running TP-CDS, it turns out running it on a fixed cluster was 37% cheaper than auto-scaling. And I'm using kind of just default parameters that Databricks recommends. And so how do you know if you should use auto-scale cluster or a fixed cluster? I don't know. Another thing is like instance types are hard to figure out. We took TP-CDS, we ran it across 15 different machines on Amazon. The span of costs went to 2x. So you could be paying double the bill just because you picked the wrong machine. Another example, Photon. There's a talk here on Photon and what it does. Photon is also hard to figure out. Is it worth it? Turns out for TP-CDS, using kind of the instances we were looking at, if you kind of do the math, you have to be faster by at least 20% for it to make sense. Meaning if you use Photon and you're only 10% faster, you're actually spending more money to use Photon. And so it's not worth it. And this 20%, by the way, is specific to your workload. So we don't know if this 20% applies to your jobs. Now, those are kind of like 3 examples, but there are many other kind of confusing things. A lot of questions we get about are on serverless. Does that make sense? Serverless is typically really good for convenience. There's usually a surcharge on top. So does that really solve your cost efficiency problems? There are other things like Graviton, new releases of Spark. What if my data changes? What if my SKU changes? Just a lot of things can change, and this is why it's so complicated, and these are not fixed in time, right? So it just doesn't make a lot of sense for an engineer to try to just figure this out and sit on top of it, because they have other stuff to do. And the heart of the problem is that optimization is workload and goal specific, right? Maybe it's cost savings, maybe you need this thing to run super fast, and you're okay with a doubling the bill, right? It's very dependent on your workload and what you're trying to do. And that's why it's so hard, because there's no global solution. So that's why we kind of built Gradient. Our tagline is, we make Databricks optimization goals made easy. And so here's kind of a quick screenshot of the product. How it works kind of at the highest level in terms of like the system. How does it work? So here we have our client environment up top. That's kind of the customer. And they're basically running their job just like they do right now, every day. And every time you run a Databricks job, you can output your Spark event log. That's the log that we consume. So we consume your Spark event log and your cluster information. That then gets shipped over to the sync side, where we then ingest that information, we run our simulations, and then we take your input, like what's your goal? Is it was much better than a laser pointer. But we take your goal, like maybe it's a 1 hour SLA that you want to hit, and we kind of select the best recommendation. We'll talk about how when Sean presents. But once we kind of select the best recommendation, we give you one recommendation. We don't give you like 50 things you got to look through or sift through. We just give you one magical recommendation. You take that and you run your cluster with that. And you are always in control. You can pick, like, do you want this or not? If you do, great. If you don't, for whatever reason, you don't have to take it. So you're kind of always in the driver's seat. So before we kind of get into the data science part of it, this is kind of a new product, and we wanted to show how do you actually interface with this product. So just very quickly, when you log into Gradient, you will land on this projects page, and there's only really one button to start, create project. And a project is basically a Databricks job that is running in production like once a day, for example. And that is the job we will monitor. And so we have this nice import wizard where you put in your token and your host, and we will actually automatically go into your environment and fetch the jobs that are good candidates to be optimized, meaning they meet some criteria. And once that's in, then you click on Fetch Job, and then it's imported into the Gradient system, and now you should see the names of your jobs. It should be very familiar with what you see internally inside the Databricks platform. And it's now inside the Gradient system. Now, it's not totally done yet. You still have to instrument it, and so that's why there's a setup pending step where you have to kind of go into our docs. You have to download kind of our Python library and instrument it, and I'll kind of get into that in a little bit. We try to make it as easy as possible to basically automatically and continuously send us this information that we need. And so when you do that, this is basically what you get. So let's say you send us your Spark event log for your job. On the left is, for example, what you're running with today. It ran for 104 minutes. It cost $6.62. And our recommendation says we can optimize it down to 78 minutes and almost $5, so 25% faster, 26% cheaper. And that's great, but let's say for some reason you're like, well, I don't really like this. I need a 1 hour runtime. So what can you do? So you can actually click on settings and change the SLA. You can say, okay, I want a 1 hour runtime. You set that. You click go. You get another prediction. And then what you get is now you can tune this prediction such that now it's 56 minutes. So it's underneath the 1 hour time that you wanted. And you didn't have to go in and figure it out. The Gradient basically did it for you. We tell you exactly how to do it, what instance type, what is the number of workers that you need, and a bunch of other configurations. We then give you that information in a JSON. You copy and paste that into your Databricks environment, and you can go. So it's kind of, we want to make this as easy as possible. We just kind of give you the answer. You don't have to pick and choose anything. It's just like, here you go. This is what you need to do to basically hit your goal. So just for fact checking, so we actually did run TPCDS with this, and I took that exact recommendation on that previous screen, and this is just a screenshot from the Databricks console, but when I did run that, the actual duration was 55 minutes, so it did hit that 1 hour goal, which is pretty cool. And again, as a data engineer, I didn't have to figure out anything. I didn't have to sweep or change nodes. It just Gradient basically told me the answer so I could move on with my life. In terms of how do we integrate, so right now we support Airflow and Databricks workflows, so users today basically run with this. So let's say you use Databricks workflows today. You have your Spark job that runs today on a regular schedule. And what we do is we add a second step that basically just collects all of the cluster information, the Spark event logs, and that gets sent over to Gradient continuously. So if you run this, let's say once a day, we basically get your logs every day. And then we can kind of monitor and see how things fluctuate over time. As an example, there's a company, Insider. They're an ad tech company. They're about 1,000 people large. They have thousands of Spark jobs that run daily, processing customer information. And they instrumented us inside their production systems. And they use Airflow. I won't get into the details of their schematic here, but basically every time they submit a job, they run it through Gradient to double check and to see if there are opportunities. Because their engineers are busy doing other stuff, they don't want to be sitting there monitoring and optimizing all their jobs. In terms of the overall ROI, across all their thousands of jobs, on average, we got them 25% cost savings. And on some of their most expensive jobs, we got 50% on some of their largest jobs. And so that was great to kind of see. Sorry, excuse me. And at the end of the day, we will have a dashboard which will kind of show you the ROI. We want this to be like an alert system to kind of help your engineers know, oh, hey, there's something for me to do. So for example, unrealized savings, like, hey, there's $152,000 on the table right now because you're not optimal. So this is all about kind of informing you and telling you, hey, there's something for you to do to be optimal. At this point, I'll pass it on to Sean, who will kind of go inside the inner workings of Gradient and how we built it. So, Sean.
Great. Thank you, Jeff. So Jeff was just telling you about the projects that we have. So in Databricks, you have your Databricks job, and in Sync, you have a project that maps to that job. And the goal of that project is to optimize the job for you. So I want to talk to you a little bit more about the process under the hood of what's happening in a project and in the flow for giving you a recommendation for that project. So how it starts here is on the right, we have your next Databricks job run. So you have your production job running daily. The next time it runs, you've installed everything like Jeff showed through the CLI. And when it runs, it pipes the relevant information to us, which isn't a whole lot. It's the Spark event log and some cluster composition information. And that data gets piped directly to the collection of project data associated with that job. And now you're in part of what we think of as the project loop. So on the left, you have the collection of your project data. It's the history of submissions to that project. You have the settings, things like the SLA Jeff mentioned, other settings like whether you're willing to use on-demand or spot instances. The next step that happens is runtime prediction, where we use predictive modeling to take an educated guess at what the runtime will be the next time this job runs on various hardware configurations. From there, we do a cost modeling step, and then we select a recommendation that we pass along to you, that it's in your choice whether or not you implement that in your next job run. If you do, ideally, you're realizing the cost savings that we think you can get. If you don't, that's okay. The next project, then the next run's data still gets sent to us, and we get to use that to give you more predictions in the future. So I want to go through each of these little steps here because there's a lot going on. The first one, and arguably the hardest, is this runtime prediction model. So you have this history of data, and you want to take it into your model, and you want to spit out, for every hardware configuration it might be interesting, you want to do a runtime prediction model. So it's basically a two-step process under the hood. The first is you have to intelligently select the hardware that might be interesting to look at, and then you run that through your model and do your runtime prediction modeling. And we've explored a lot of different avenues for this, some deterministic modeling. We're starting to explore more black box machine learning models right now, but this is a heavy exploration area for our data science team, and it's a really challenging problem, but one we're super excited about. And the goal here is that you have this project loop going on, and you're continuously feeding it more data, and it really opens the door for using that history of data to improve your runtime recommendations over time. I'll talk a little bit more about that at the close. At the end of this runtime prediction process, though, you have this kind of figure that I show on the lower right. You have a bunch of unique hardware configurations, and for each one, there's a cluster composition, and there's the runtime that you've predicted that it will run. From there, you go on to the modeling cost. I don't know if anybody here has tried to calculate their Databricks costs at the granularity of a single cluster, but if you have, you'll know that it's harder than you think. So what do I mean by that? So up here in the top right, we'll show like a little map of the timeline of your cluster job. You have a driver that gets turned on. You might get some on-demand workers that are added or subtracted throughout the duration of the application. You might also have some spot workers going on. And the formula at first glance is super easy for how you would calculate this cost, right? For every machine that's on that graph, you take the charge rate in dollars per hour, and then you multiply it by the time that instance was active. But this is actually a super challenging problem and not trivial to calculate for a few reasons. First, the machine hours. To extract that kind of information, you have to make multiple API calls, both to Databricks and to AWS. Even then, those API calls are time sensitive, so if you don't do it soon enough, you lose the AWS information, and you can't get the EC2 cost necessarily. Of course, you can use the Databricks runtime as a proxy, but it's not perfect, because Databricks doesn't tell you what instances were a part of your cluster when either. They just tell you how many instances you have periodically. There are other complications we've run into, like Databricks will reuse your EC2 instances across multiple clusters. So if you go to your EC2, your AWS billing, and you look for a Databricks cluster tag, that's only the last cluster that instance was a part of, but it may have been part of multiple clusters before that. It's another dimension that makes this really challenging to do. And of course, the machine hours are different for Databricks and for AWS or your other cloud provider. Overall, this is challenging because you're working with root data that isn't 100% accurate. So there's inherently some uncertainty here. Charge rates have their own complexities, time dependencies for spot pricing, regional dependencies, reserved instance pricing, and so on. So there's a lot of work we've put into our cost modeling, both in estimating the cost of the logs that you give us and also estimating the cost of our recommendations that we give, because we really need those to be as accurate as possible to give you a good recommendation. Okay, so first we predicted runtime for these configurations, we predicted cost, and now it comes to making a recommendation to pass along to you. So the state we're at here is in the top right? We have a bunch of points. Each point is a unique hardware configuration. You have the predicted runtimes and the predicted cost for each. The first thing that happens is if you have an SLA with your project, it cuts off all the points to the right of your SLA. If we think that cluster is going to run for too long, we're not going to recommend it to you. And from there, it's pretty straightforward. If we can reach your SLA, we're going to give you the cheapest one we can give you. And so our recommendation is lowering your cost while maintaining the business needs for that job that's running. And here's just a little snippet of what that hardware looks like, or what that output looks like. You have a runtime and a cost we've predicted. You have things like the driver type and the worker instance type, the number of workers, and so on. So this is it. This is what comes out of our recommendation model. You're fed this type of information, and then it's up to you and whatever CI pipeline you have for implementing your infrastructure, whether or not you want to integrate this recommendation for your job's next run. And of course, the platform, the UI pictures Jeff was showing you before, those give you insight into how performances change over time, when recommendations have been executed, things like that. So I want to talk a little bit about the results so far, because I mentioned that this is a really challenging data problem. So there are all these burning questions of how well does it actually work? How did you build something like this without actually having customers using this integrated loop going on? And this was a really challenging problem that we worked really hard on, and we have some results that we're proud to show. So way back when we first started this project, it was just a few data scientists doing stuff we really didn't know about. Before we had a proper engineering team that could build the systems that make this into an actual functional product. And since we didn't have a product that people could deliver data to, we had to effectively build a mini product and start using it for ourselves. So what we did is we built this bank of jobs, this bank of Spark applications that we can pull from and then run them on a hardware selection of our choice. And then we built an orchestrator that could run many of these instances in parallel. So we could effectively test our product at scale, but internally to sync. So the process is here. You have this orchestrator, you have a bunch of instances running in parallel, and you're choosing your initial hardware, your application. You do an initial run, which you can think of as your cold start run, and then you feed it into Gradient, and then you implement the recommendation, and you run the application again. So this gives us a good, solid footing for starting some internal testing and product validation. All of this data we have piped into our Databricks environment. It's ingested into a Delta Live pipeline, and that lets us look at data nice and easily. It's been a really nice process for us. So the key for the first validation and early development, of course, is comparing this run 1 to your run 2. And you can imagine, of course, in the full product, you're continuing these iterations indefinitely as long as the run is in production. So what does that process look like? So you have your run 1, you have a point that is your actual run time, how long that application took to run. You have your run 2, where you have both a predicted and an actual, and your SLA, of course, shows up as a horizontal line in this plot. So you can do some analysis with this already, right? You can measure your runtime prediction accuracy. If you've run this at scale, you can run statistics on your prediction accuracy. You can assess your SLA target performance. If you have, as the database grows, you can do more and more pattern analysis for when your prediction accuracy is good, when it's not as good, and of course that helps inform you how to shape the product to make sure you're always giving recommendations that you believe are good. On the flip side, you also have the same plot but with cost, right? Your actual cost, which as I described is actually pretty hard to get, and you have your predicted cost, and you can do validation of your cost estimation model. You can assess the product performance, and you can see end-to-end how things are going. So this was a great help for us. And in this one-in, one-out paradigm, we actually have results we're really excited about. So I'm showing here some aggregate data that we have internally for how the cost reduction performs without an SLA constraint for 2 types of input clusters. One is an auto-scaled input cluster with varying min and max parameters, and then the other is a static input cluster. And what we found is for these auto-scale input clusters, 87% of our recommended runs, that's that second run after gradient, resulted in a cost reduction. It's not on here, but the median actually is about minus 30% cost reduction in 30% cost reduction. The results for the static input clusters were a little bit less exciting, but they were still good. It was still above average. We had 65% of those runs resulted in a cost savings. And at first maybe that's not so exciting, but I'll remind you that that's just our one-in, one-out log. That's your first try at optimizing that cluster. And as this data collection process goes, it's only going to move in a better direction for you. So we're really excited about where this is and where we're taking it. A number of very early customers used us in this kind of paradigm of one in, one out, and they had excellent experiences. People who either, on both EMR and Databricks, who either found cost reductions or speed ups at about the same cost, or in some cases both. So we definitely at this point know we're onto something. So to wrap this up, I want to talk a little bit about the vision or the future. I've set the stage for the data we're collecting and how we might use it. And so what are some of the cases where we can really leverage this internal design to help you all save money on your clusters? So take this case, which is a very real case. You have data size. Say you have a daily running job, and every day you ingest some data, you do some processing, you spit out a report or some other table or something. But every day within the month, that data size grows. Maybe you're looking at your AWS billing, for example. That's a very real case. Well, that data size grows throughout the month. So rationally, every time your data size has changed, there's a new choice you could be making for your cluster that would optimize the cost for that run, right? Every time that production job runs, there's a new opportunity for optimization. But of course, an engineer's not going to do that. That's so much time, and it's a super hard problem. They have more important things to do. So you can imagine a scenario like this where you have a tool like Gradient plugged in every day making decisions that help keep your costs low while still hitting all those targets like SLAs. This is a particularly interesting case too, because if it's a monthly cyclical, at the end of every month it goes back to 0. So if you have a history of data, you can also predict that happening, right? You say it's the first of the month. Your cluster size can be reduced by 10x. Imagine using 10x larger cluster than you should be. It's a lot of money you'd be saving. So there really is a future of continuous value here. As that data grows, you can imagine all the vectors of optimization that you can implement so that over time your cost is reduced and it's kept at a low value, even as underlying things like the data size changes. It also lets you try out new things in an easier way, say new instance type offerings, new runtime engines provided by Databricks. Gradient would be an avenue to test those things while keeping your job stable, always searching for the most optimal cost for you. It's an important thing to be doing all the time, and it's something that most of us just don't have time for. So with that, I'll turn it over to Jeff again to close this out.
Cool, thanks, Sean. So this is the last slide, just to kind of reiterate. Those like 4 pain points I mentioned that data engineers had, we tried to solve them with Gradient, right? So 1, we make it really easy so you know how to optimize very easily. 2, we show you when to optimize so we can actually alert you as we're constantly monitoring it. 3, we help you hit your goals at your lowest cost. If you have a runtime goal, we help you hit that. And 4, I think most excitingly, we can do this at scale, right? We provide you a Python programmatic access so you can apply it to all of your jobs all the time. And that's, for example, how Insider was running this. And so that's basically it. Gradient is available now. We just released it last week. Folks can go and buy themselves. We have great docs. It's self-serve, so you can try it out yourself. And we would love your support and feedback. Please let us know how it is. And if you want to do a deep dive or an actual hands-on demo, feel free to chat with us at our booth. And that's the QR code to our site to check out Gradient.